Hi everyone. Today we're going to be talking about Einstein's special theory of relativity. This is a good model of how the universe works. It manages to explain pretty much all the stuff that we can see in space, aside from things to do with strong gravitational fields and accelerations. So using the special theory of relativity, we can explain some of the effects that happen when we move at very fast speeds. And we can also see why the ether is not necessary. To begin with, we'll be talking about Einstein's postulates. These are three assumptions that Einstein made in order to work out his theory of relativity. Because the theory uses such high speeds for anything to be able to happen, we can't replicate it with real experiments very easily. And certainly in Einstein's time, it was completely impossible to observe any of the effects that he was predicting. Now, as we know, if we can measure the speed of ether, then we're violating the principle of relativity, right? Relativity says that it's impossible to tell how fast we're going without looking at an outside frame of reference. But if the ether exists, it means that the speed of light will change depending on how the ether is moving with respect to you. We can see that the two beams of light at the top and the bottom of this animation move at different speeds because they're being pulled by the ether. So in the early 1900s, Albert Einstein thought about this conflict between ether and the principle of relativity. And in the end, he figured out a way to solve it. First of all, he presented a situation as a thought experiment to prove that the two ideas were completely incompatible with each other. A lot of his thought experiments start the same way. We have a train traveling at, or almost at, the speed of light. So if we're sitting on a train traveling at the speed of light, and we hold up a mirror, what do you see? Do you see your reflection? Or do you not see your reflection? In the ether model, the light coming from your face is sort of blown back by the ether as the train rushes through it. This means that because light can't sort of outspeed the ether, it can never reach the mirror and never reflect. This means that if the ether exists, it's possible to tell how fast you're moving by holding up a mirror. And if you can't see your reflection, that means that you must be traveling at the speed of light. But of course, the principle of relativity says that we can't figure out our speed if we don't have an outside point of reference. So the principle of relativity states that it is impossible to detect any motion in an inertial frame of reference. You can't tell if you're moving forward or backwards, or if you're not moving at all. But ether provides a way to do this. All we need is a mirror. So Einstein realized that light has to travel at the same speed in all frames of reference if the principle of relativity holds true, right? So that means that you will see your reflection if you hold up a mirror in a train traveling at the speed of light. If you can see your reflection and there's no delay or no funny business, then we won't be able to tell how fast we're going, right? We see our reflection just as if the train was stationary. So what if we have two people in two different reference frames that are measuring the same beam of light? Maybe we've got someone stationary with a light speed camera, and we've got someone moving at high speed with a light speed camera. How would they measure the speed of light to travel? Would it be different for both people? Well, as a matter of fact, no. Because the speed of light is invariant, it doesn't change whether we're in a train traveling at the speed of light or if we're stationary. Then both observers, moving and stationary, have to measure light at the same speed. Which is odd, right? You would expect the person moving to measure a different speed than the person who's stationary, because that's what we've learned in the Newtonian physics that we were studying in year 11 and most of year 12. So if the speed is the same, even though they're traveling at even though the observers are traveling at different speeds, then this must mean that they are witnessing different distances and times. Otherwise, we wouldn't be able to explain how they can measure the same speed. So Einstein's three postulates are as follows. Firstly, the laws of physics are the same in all frames of reference. All inertial frames of reference are equivalent. It's impossible to tell if you're in an inertial frame of reference by conducting an experiment. So you won't be able to tell whether you're moving forward or back, or if you're just stationary. Secondly, everyone always observes light to travel at the same speed through a vacuum. That is, the speed of light is invariant. No matter how fast you're moving, you always measure light traveling at the same speed. And finally, the luminiferous ether is not needed to explain light. If it was needed, then the second postulate could not hold true, because the speed of light would be affected by the speed of the ether. So with these three postulates, these three base assumptions, you might say, Einstein was able to figure out his entire theory of relativity, which is able to predict very accurately how objects will move at high speed, or how they'll behave at high speed. This set of rules and laws is called Einstein's special theory of relativity. There are a number of different parts to it, and we'll be going on to those in the coming lessons. It is called the special theory of relativity because it only works for special cases. It doesn't work for all cases. Remember that the principle of relativity only applies to inertial frames of reference. That is, frames of reference that are not accelerating. Einstein's special theory of relativity only handles these. So the theory can only describe motion in inertial frames of reference. It cannot describe motion in non-inertial frames of reference. The special theory of relativity deals only with the special case of inertial frames. If we want to deal with the general case of all frames, then we'll need the general theory of relativity. But that's not covered in Year 12. Now in Newtonian physics, we have a constant quantity that is unchanging and invariant, and that is time. Time doesn't change depending on how fast you're moving, right? Whether you're traveling at 100 kilometers per hour or whether you're stationary, 1 second is still 1 second for everyone. In Newtonian physics or classical physics, time is invariant, but not so for relativistic physics. In relativistic physics, or Einsteinian physics, I suppose, the speed of light is what is invariant. A second for someone traveling at almost the speed of light will not be the same as a second for someone stationary. But the speed of light, the speed of an electromagnetic wave, will be the same for all observers, regardless of how fast they're traveling relative to each other. So this leads to some really weird and interesting effects. It means that we can predict exactly how long a second will be for someone traveling at high speed, and figure out how different it will be to someone who's stationary with respect to some outside point of reference. So let's take a look at an example. Suppose that, once again, using Einstein's sort of classic thought experiments, we have a train traveling at almost the speed of light. So close that you can't really tell the difference. Now, if a passenger holds up a mirror, then because of the principle of relativity, they're going to observe their reflection, right? They can't tell that they're in an inertial frame of reference that's moving with respect to an outside point. And because they can't figure out their motion, light has to travel normally. So it very, very quickly reflects from the mirror and comes back to them, right? It's almost instant. But suppose that instead of being the passenger on the train, we're someone outside the train. In this case, because the train is traveling so quickly, the light has to try and catch up to the mirror. It takes a very long time for light to get all the way from the left of the animation into the mirror. And this at first seems very strange. It means that from the passenger's point of view, the event of him seeing his reflection takes a very, very short time. But to anyone outside the train, the same event takes a very long time. So we can see that the time that events take inside the train and outside the train will be different depending on how you're moving. So we can see that the time measured by each observer is not always the same. In classical physics or Newtonian physics, time is invariant. It doesn't change. But in relativistic physics, it is not invariant and it can change. So it turns out, and we'll be getting onto this in later lessons, that distance is also variable. So if we have the distance between 2 points, if we use classical physics, Newtonian physics, then no matter how fast someone is moving, they'll always agree that the distance between 2 points is going to be the same. In relativistic physics, that all changes. The distance between 2 points will depend on exactly how fast you're traveling with respect to them. But you can't say that one is more correct than the other. In fact, both observers are correct in their own frame of reference. It means that even if two observers always get different results, they'll always be correct in their own frame of reference. Just like in classical physics, two observers, one of which is moving relative to the other, might measure different speeds for a moving object. So that's the end of the theory. Let's go on to some questions to test your knowledge. Question 1. Alice is in a bus moving at constant velocity from left to right. She tosses a ball straight up from her perspective, and it goes up, and then something else happens. Does it go down or does it go across? Well, we'll find that out when we're answering the question. So its path is also observed by Bob, who is outside the bus, standing still. Now, what do they see? Well, first of all, let's ask ourselves what would happen if we tossed a ball straight up and we were not moving. We're in an inertial frame of reference that is stationary. The ball's going to go straight up and then come straight back down, right? Now, if the principle of relativity holds true, then that means that if we're in a bus traveling at constant velocity, then we won't be able to tell the difference between that bus and a stationary bus. So Alice is going to see the ball move straight up and straight down. So we have A or C as our options. So what does Bob see? Does he see the ball moving from left to right or right to left? Well, he'll be seeing it move inside the bus, and the bus is moving from left to right, so the ball will also move from left to right. That means that A is the correct answer. Question 2. Which option best describes the principle of relativity? Is it A, non-inertial frames of reference are accelerating? B, no experiment can be performed in an inertial frame of reference to prove that it is moving? Is it C, no experiment can be performed in a non-inertial frame of reference to prove that it is accelerating? Or D, all inertial frames of reference move at the same velocity? Now, what is an inertial frame of reference? It's a frame of reference that's traveling at a constant velocity, but it doesn't have to be the same as all other inertial frames of reference. Sure, you can say they're equivalent, but you can't say that they're all moving at the same velocity. We also know that non-inertial frames of reference are accelerating, but this doesn't really relate to the principle of relativity. The principle of relativity says that we can't tell whether an inertial frame of reference is moving, right? And the one that's closest to that form is in fact B. No experiment can be performed inside an inertial frame of reference to prove that it is moving. right? If we measure the speed of light, it's going to be just the same as if we were stationary. If we do any other experiment that you can possibly think of, the results will be just the same as if the frame of reference was stationary. So we can't prove that an inertial frame of reference is moving. Question 3. Earth sends a microwave message to a spacecraft that is traveling directly away from Earth at 0.4 c. How fast is the microwave signal moving relative to the spacecraft? So we can draw a diagram here. We have planet Earth, and we have a rocket moving away from it at 0.4 c, a little bit under half the speed of light. Now the Earth sends a microwave message, an electromagnetic wave, at a speed of c relative to the Earth. So how fast is this beam of light going relative to the spaceship? Now if we were using Newtonian physics or classical physics, then what would our answer be? Well, we'd say that because the light needs to catch up with the spacecraft, it seems to be moving slightly slower, right? So we subtract our 0.4 c from the 1 c, and we end up with 0.6 c. But this answer is wrong. Microwaves travel at the speed of light. They're an electromagnetic wave. And Einstein's special theory of relativity states that the speed of light is the same for all observers, regardless of their frame of reference. So the speed of an electromagnetic wave is constant. Doesn't matter how fast you're moving away from the Earth or how fast you're moving toward it. You will always measure the speed of the microwave signal as c, the speed of light. Question 4. Why did Einstein use thought experiments instead of actual physical experiments to develop his theories? It took a long time for Einstein's theories to get any credibility from other scientists. Part of this is because you couldn't really show them any experiments that Einstein had done. You could only ever show them his thought experiments. So sure, if he had done proper physical experiments, his theories would have got a bit more support, right? Well, there's a problem with that, and that's that the experiments are very, very hard to do. Special relativity and the effects of it on objects can only be seen when we have different frames of reference moving at very, very high speeds, right? It means that we need to be moving at, half the speed of light before we begin to see any noticeable effects. And the thing is, it's really hard to get half the speed of light as a speed for anything. Even today, the only things that we've managed to get to that sort of crazy high speed is tiny subatomic particles, like protons or electrons. We can get those to half the speed of light. We can't get anything else to half the speed of light. And so in Einstein's time, it was pretty much impossible to accelerate anything to that sort of speed, which means that it would be impossible to do one of these experiments. And instead, we'll have to use the power of imagination and do thought experiments instead. Question 5. If a passenger on a train traveling at the speed of light holds up a mirror, will they see their own reflection? Now let's think back to Einstein's postulates. The laws of physics are the same in all inertial frames of reference. So, will you see your own reflection if you're in a stationary frame of reference? The answer, of course, is yes. And so in any inertial frame of reference, you must see your reflection. It is impossible to measure the speed of an inertial frame of reference without some sort of outside point. Part B asks, if you hold up a mirror, will an outside observer see the reflection? That is, will the light from your face ever catch up with the mirror? And the answer is, according to the outside observer, the light from your face is traveling at the same speed as the train, so it will never catch up. That means the outside observer will never see the light catch up and bounce off the mirror. That's because from the passenger's point of view, the train is traveling at light speed, and the light from your face is traveling at light speed, and so they can never meet up. Well, that's the end of the questions. So we're at the end of the section. In this section, we've learned about Einstein's postulates and how they gave rise to his special theory of relativity. In the next section, we'll be looking at what the theory of relativity has to say about simultaneity.